Hello everyone. In this video, I'm going to be going over both my Master TA lecture and assignment overview for Module 10 in CIT 247. The topic for this video will be VLSM. Lecture slides 2 to 7 will be from Dr. Rana. I want to thank him for these lecture slides. I didn't make my own this module because Rana's were actually really good. They actually really helped out and they really summarized the topic well. So I decided to use them. I did add an additional one though, which I'll show you soon. But I'm also going to provide an overview of VLSM that's similar to what you're going to be doing in your lab. So it's kind of an assignment overview as well. Or at least what I'm going to be doing in the video. So let's discuss VLSM together. VLSM stands for Variable Length Subnet Mask, where the subnet design uses more than one mask in the same network. This means that more than one mask is used for different subnets of a single class, A, B, or C network. So for example, you can have like a class C network, and you've been using /24 for a lot of your assignments. So in VLSM, you actually be using stuff like /24 alongside /25 in the same like big network, but each LAN will have its own subnet mask basically. So this is used to increase the usability of subnets as they can be of variable size. So in other words, the purpose of VLSM is to reduce the number of subnets we use, or the number of IP addresses we use. You've probably already heard that IPv4 has a very limited number of addresses. Therefore, for especially large networks, it's very important to conserve the addresses used. So you want to be able to stretch them as far as you can. And that's how like the public addresses are done. They're VLSM'd, so they're stretched out as far as they can go. So VLSM can also be defined as the process of subnetting a subnet. In other words, in subnetting, you're basically breaking a network into little pieces. So in VLSM, you're basically breaking a network. You're breaking a subnet into multiple subnets. So there's a specific procedure we go through in implementing VLSM. So in VLSM, subnets use block size based on requirements, so subnetting is required multiple times. So in other words, you're basically given a block, like a classful block, like 192.168.0.0/24, and then it's your job to break that block into multiple subnets, depending on the required host numbers in your department or your network. So we're given an example by Debrana with an administrator that has 4 departments to manage. So the first one is sales and purchase with 120 computers. The second is development with 50, accounts with 26, and then finally the management department with 5 computers. So basically each of these departments have very different host requirements. So that's where VLSM comes in. So as I said, we're given a block. So in this case, it's the 192.168.1.0/24 block. And then we need to break into multiple subnets based on the host requirements for each of these departments. So step one, first, one of the steps we use to do this is, excuse me. So the general premise here, what we're doing is, for each segment, select the block size that is greater than or equal to the actual requirements, which is the sum of host addresses, broadcast addresses, and network addresses. So in other words, basically the goal here is to take a CIDR notation mask, take a mask from here, and then basically what you do is you correlate the number of hosts that this subnet can support, and then you assign it to a department based on its host needs. So for example, sales and purchase department needs 120 computers. So you go to a table like this, like the one Rana provided, and you see which subnet mask can support at least 120 hosts. So we see /26 is too small, it only supports up to 62 hosts. /25, however, supports 126, so therefore that department uses the /25 mask. So the first step in VLSM is basically to order the departments by host need from largest to smallest. So sales and purchase has the largest number of required hosts, therefore it goes first, followed by department, accounting, and then management. So basically, you want to find a subnet mask that matches this, the biggest department, and then you go from the next smallest to finally the smallest, from largest to smallest. So the highest IP available has to be allocated to the highest requirement. So the sales and purchase department gets 192.168.1.0/25, which has 126 valid addresses. It makes, in other words, it easily supports the 120, the 101, excuse me, it supports the 120 host requirements of the sales and purchase department. Important point here is you need to make sure you remember the subnet mask, like the decimal notation mask that corresponds to each CIDR mask that you select, because you'll be actually implementing OSPF in your lab. So this is actually your lab document. So you're given these 4 networks here in your lab, and you'll need to do VLSM for them. Once you chart that out on like paper or a notepad or something, you'll then need to actually configure configure it in GNS. It says it right here. Once you design your map on paper, implement it in GNS. So one of the major steps is configuring OSPF. You actually need to configure OSPF with your VLSM design. Then therefore you'll need to memorize your subnet masks, or you need to write them down. I mean. So in the next segment after the first one, which was sales and purchase, we're now gonna subnet for the which one is it? Development department. So it has 50 hosts. So the subnet mask we're going to use is /26. If you go back to the table, it easily supports this, whereas /27 doesn't. So you basically just fill out like that, and then you do the same for the other 2 departments. The third one uses /27. The final one uses /29. So let me pull something up here. I want to show you all something before we continue. So I have this notepad right here. I'm going to zoom it up a little bit. So if you look here, I've performed VLSM on all of the departments based on their host requirements. So this is to demonstrate an important concept of VLSM. So the reason why we start with the largest network is because it wastes IP addresses to use a smaller one and then use a bigger one. So let me explain something here. So if you do for every 4, so let's do some multiplication here. So we say we're doing every 4 and then every 16. So if we start a subnet like that supports 4 hosts, we start with that one, and then we need to do a mask that supports 8 hosts. We have a problem here. This is just a theoretical example, by the way, but we run into a problem here because we have 4 here. So the mask that takes up 4 hosts takes up 4, but the next one that takes up 8 has to start on a number that is a multiple of 8. So therefore, we have to start with 16 because let me see. I'm sorry. Let's start with 0 on here. That makes more sense. I'm sorry. So say the mask that supports 4 hosts starts from 0, and then we go from 0 to 4. If we have a mask, we need to use a mask that it supports 8 hosts. We have a problem here because we've already used 0 to 4, so we have to start with 8 to 16. We waste 4 addresses between the 4 and the 8. So that's why it's important to start with the bigger one, and then you work your way to the smaller one, because you minimize waste that can be you minimize the waste that comes from starting with smaller ones and going to bigger ones. So an important point here when you're doing the subnetting is you want to write down the subnet ID with the mask, and then you want to write down the broadcast address. So basically when you're doing VLSM, you need to keep track of where the next subnet starts, or the next available address that you can start from. So /25 takes up 128 addresses, including the subnet ID and broadcast address. So you go from 1.1 excuse me, .1.0 to .1.127. So the next available IP address is 192.168.1.128. That's the next available subnet ID. So /26 needs to start right on that address. And then you do that again for the others. So you basically write down the broadcast address, and then you use the next IP address as the subnet ID. This should pretty much always work whenever you're doing biggest to smallest. So basically, that's what you need to do when you do the VLSM. You can't just write down a mask. You need to know where it ends, or You need to know where it ends. You need to write down the broadcast address, and then start from the next available subnet ID. So one other point I wanted to bring up, VLSM and point-to-point connections. So when you're subnetting for router point-to-point connections, you can use the following pattern as a shortcut. So basically all point-to-point connections between routers use /30. This is because there's a total of 4 addresses in the /30, the subnet ID, the 2 usable IP addresses, and the broadcast address. You don't want to use anything bigger than that because it's a major waste for point-to-point router connections. Basically, there's just 2 addresses that need IP addresses. So let's use an example with the 192 and 168.0.0 block. Excuse me. So every subnet ID is a multiple of 4. So you start with 0, and if you see on the other side, I have 4. So every subnet ID in a point-to-point connection area is going to be a multiple of 4. So after you start with that multiple, you can put the first 2 addresses, or put the 2 addresses, and then the third one you mark as the broadcast address. Basically, you can kind of ignore the broadcast address. Just know that in the point-to-point connection, every subnet ID is going to start with a multiple of 4, and then the next 2 addresses are going to be your usable ones, the ones you're going to actually allocate to the interfaces. So now that we have that out of the way, now that we explained VLSM, we're going to take a look at the assignment for this week. So you're going to be allocating for a you're going to be allocating some IP addresses or subnet masks to these 4 networks here. So you're given the private network of 10.0.0.0, and you need to use VLSM to break this network up into multiple pieces for these networks. So as before, you want to start with the 2 biggest ones. They're equal. You can start with either one. You need to provide a subnet mask for each one. Then you need to provide a subnet mask for Chicago, and then finally for Dallas. Now, I'm not going to do that for you. I don't want to do your work for you, but basically I'm just going to give you a hint. Just start from the biggest ones, then work your way down the sides. One way you can do this is by writing this stuff down in a notepad, like I'm doing here. Or you can print out this diagram, and then write out your subnets. You also, however, need to make sure you use the Class C network of 192.168.1.0 for your point-to-point connection. So basically, let me zoom this out a little bit. So basically, your point-to-point connections are going to be here, between the squiggly lines between the 2 routers, and then your these networks here, these 4 networks here, are going to be your endpoints, these right here. So basically, you're going to connect a computer, like a virtual, one of the VPCSs, to your routers in your network, and then you're going to connect all the routers together. So, diagram asks you to use serial links for your point-to-point connections between the routers. And then you need to assign IP addresses to the serial links and fast Ethernet links. So basically, it would be best to put computers at the end of each of these endpoints, these fast Ethernet endpoints in your network. So to show you this, I made a little example here. It's similar to what you're going to be building in GNS after you do your VLSM stuff, but make sure you put a little computer at each end. So the serial links look like this. They're the little red squiggly lines. Please be sure to use these between the routers, and then use fast Ethernet between all the computers in the router. So we're going to do some VLSM together here. So subnet blocks given, we're going to be given 2 subnet blocks. We're given the 192 and 168.2.0 for we're given that subnet block for the endpoints, and then we're given the 10.0.0.0 block for the points between the router and the computers. So let's go ahead and start. So the first endpoint, the 2.0. So this is a pattern of 4, 168.2.4. So you keep moving on and on with that. So let's go ahead and plot those down to 168.2.0/30. So basically, you can actually mark your subnets like this in GNS with this little pencil and pad button. And then 192.168.2.4/30. Oops, sorry. 30. And also, if you want, you can do something like this. Like you could put 0.1. So you can like mark your interfaces like this for you to remember. 2. And then you can do the same here. So it starts with 4. The subject down here. This side starts with 4. So we do dot 5. We do dot 6. So that's basically how you can plot out these. I'll do the rest of them for you. So 192.168.2.8.0, sorry, slash 30. So finally we're going to do 192.168.2.12 slash 30. So that's how you plot out your endpoints. So basically all you need to remember when you do that is put down the subnet ID for your endpoints. It's going to be always going to be a slash 30 mask. It's always going to be a multiple for the very last number. Your endpoints, the actual endpoints themselves, need to be the next two numbers after that subnet ID. And then you just skip the last address in the subnet, that's the broadcast address, and then you move on to the next multiple of 4, and you repeat the process. So slash 8, or the dot 8 would be dot 9, and dot 10 on each side here. So I recommend doing this little dot 9, 10, stuff like that. I recommend putting like the little addresses down because it can help you keep track of them so you don't accidentally put a different address or put a number down that isn't right. And it also helps you keep track of which address goes with which interface. Let's put a comma there for some reason. There we go. So that's our endpoints. So, but that doesn't take care of the routers. So, I put the host requirements on the computers. So I'm going to subnet those out for you. So we're going to demonstrate how to do that together. So let's see here. Now this website here, I'm going to provide a link in the description for my page here for the lecture, but this is an excellent page. This website is excellent because it actually lists the CIDR mask and lists the subnet mask, like in the dot decimal notation, and then finally the number of hosts it supports. So this is excellent. This is an excellent resource for this module or for this lab. So let's check our host requirements here. We have one that needs 5,000 hosts, another network that needs 2,000, another one that needs 1,500, and then finally one that needs 250. So this PC basically is representing all those computers. That's why I put them like there, and I named them with the host requirement. So we're going to start with one network that needs 5,000, the R2 network. It needs 5,000 hosts. So you want to start from biggest to smallest. So we see that slash 20 is too small. It only supports up to 4,094 hosts. Slash 19 is what we need. So let's take our notepad here. Oops. So slash 19 is what we need. So we're going to start with 10.0.0.0 slash 19. So we need to figure out the broadcast address for this thing here. So let me see what that is. So 10.0. So let's do a little subnetting practice together. So slash 16 is the first classful network. So slash 17 has a magic number of 128, 1864, and then finally the slash 19 has a magic number of 32. So when you start with the very first subnet, 32 is basically basically 0. The subnet ID starts with 0. So we find the broadcast address, we add the magic number, and then subtract 1. So that's going to be 31.255. So that is going to be the broadcast address right there. So basically what you do is you take the mask, you recount what you find the interesting octet, which is going to be this third one right here, and then you figure out which magic number correlates to this mask. So it was 32. So the set ID already started with 0, so we don't need to worry about figuring that out. But we need to figure out the broadcast address. So we just add 32, subtract 1, and then we get our broadcast address. Now the reason we need to find the broadcast address, as I said before, is we need to know what what is the next available subnet ID. So that's going to be 10.0.32.0. Then we need to figure out which mask is going to work with it. So let's see here. So next biggest network is 2000. Needs 2000 hosts. So we take a look at the website here, and we see that the mask that meets this requirement is /21. It supports up to 2046. So we want to find the subnet that has the supported host number that is closest to our requirement, is either equal or closest to it. So /21. So the broadcast address for that, we need to figure that out. Interesting octet is still the third one. So we start with 32 as our subnet ID, our magic number. So this one was 32. Let's see here. Let me think here. 16 should be 20, and that means 8. So we do 32 plus 8 equals 40 equals 39.255. So that is our broadcast address for this network. So we need to go back here and see that the next host requirement is 1500. So let's see here now. 1500. So that one's too small. Let me double check that. Yes, 1500. So this network is too small, but this one meets the requirement. So we need to do another /21. So 10.0.40.0/21. So excuse me. So we basically do the same thing. 40 plus 8 equals 48. Subtract 1, we get 47. Okay, final network. It's 275. We need 275 hosts. So let's go back to the diagram here and double check that number. 275. So 25 is too small. This is too small. So we need /23. Let me triple check. I'm sorry. 275 hosts. So 254 is too small, but 510 is big enough. So /23. So we'll do. Oops, sorry. So our next available subnet ID is 48.0/23. So we need to now we don't really need to figure out the broadcast address here. It's not that important. But let me see. We can go ahead and do it anyway. So the magic number here is going to be 2. So the broadcast address is 49.255. So that basically that's basically all there is to VLSM. You just take the required host number, you compare it, or you find the subnet mask that matches it, you figure out the broadcast address, which helps you figure out the next available subnet ID, and then you apply the next mask and you keep going on until you plot the entire network. So we can go ahead and put these down. So biggest one here, 10.0.0.0/19. Yep. And then 32.0. Let me check the mask. 21. So this network needs that one. 10.0. I think 40. Yes. 40.0/21. And then finally 10.0.48.0/23. Okay then. So that's basically how you do VLSM for your assignment. And this is an example of that. Now, make sure you do OSPF for your lab. I'm not going to actually type it into the router, but let me show you a little something here. So if you look back at my Lab 7 command guide from the OSPF module, you can review the commands you need, but let me show you what something you need to consider when you do this. So when you go to make your network command, so network, basically you just use the subnet. So however, you need to use a network command for each subnet that a router is connected to. So each router is going to need you to do 3 network commands in OSPF. So network 10.0.48.0. Then you type the subnet ID or subnet mask, sorry. Oh, actually you do the wildcard mask. Whoops, my apologies. 0.0. Let me see. I think that's 1.255. Area 1. But the other 2 networks, however, have a very simple wildcard mask. So network 192.168.2.8 0.0.0.3 area 1, then network 192.168.2.12 0.0.0.3 area 1. So that should be the wildcard mask. So a slash 23 has a 254, so that should absolutely be the wildcard mask. So basically you would type these commands on router 4. So this would be your network command. So when you go to do OSPF, you would type router OSP, you go enter comp T, type router OSPF1, and then you would type all 3 of these network commands. So basically each router needs 3 network commands for OSPF to work properly for all these devices. That's basically it to this lecture. Thank you for watching. If you have any questions during this or for this lab, let me know. I'm more than happy to help you. Thank you all again and have a good day.